Hello everyone, welcome to this video. In this video we are going to look at more examples of groups. So let's start with our next example. Here we consider a set in which we have all 2 cross 2 matrices such that the entries or the elements of that matrix, they are real numbers. So that means A, B, C and D, they should be real in nature, and moreover the operation that we are taking is component wise addition. So we are adding the first element to the first one, so this is added to this one, the second element is added to the second element, the third is added to the third, fourth is added to the fourth. So you see, this forms a group under this operation of component wise addition. How this is so? Because the first thing that is there is the closure property, that is surely there because this is again a 2 cross 2 matrices, and these are all real numbers because the addition of real numbers is real, therefore this holds the closure property. So this matrix also belongs to the same set, right? The next thing that we can see here is 0 0 0 0, that zeros are real number, it is a 2 cross 2 matrix, so this forms the identity of this given group. Why? Because if you add any A, B, C, D element to this identity element, which is 0 0 0 and 0, what you will get? You will get A, B, C and D as the answer, right? So this 0 0 0 and 0 forms the identity of the given group. And moreover, what is the inverse in this case? The inverse in this case for an arbitrary element A, B, C, D, it would be the negative of A, because we want our one element from the group is A, B, C and D. So here we want something so that it is equal to the identity, which is 0 0 0 and 0. So what should be this number? When we add this to this, we should get 0, so it should be minus A. The next, when we add this to this, we get this 0, so it should be minus B. Next is when we add this C to this number here, we would get this 0, so it should be minus C, and similarly it should be minus D. So this is the inverse of each of the elements which is a member of the given set. Hence this form a group under component wise addition, right? So you saw the first example where we have used the set of matrices as a group, right? For the next example, you can consider this set. We are again taking the set in which we are taking 2 cross 2 matrices A, B, C, D. All A, B, C, D, they are member of real number set, so that means all of them, they are real in nature. And moreover, in this case we have one more condition, that AD minus BC should not be equal to 0. Now remember, what is this thing? This is the determinant of the matrix A, B, C and D, right, which is equal to AD minus BC. So in this case we are saying the determinant of the given matrix, whichever matrix we are taking, that should not be equal to 0, right? And we are calling this matrix by a special name. We are calling this to be GL2, R, right? Now what does this mean? It means that it has a special name in which we say it is a general linear group. So G stands for general here, L stands for linear here. So general linear group of 2 cross 2 matrices. So this represents the order of the matrix here. So it is a 2 cross 2 matrix, and all the entries are taken from the set of real numbers. So that means A, B, C, D, they are taken from the set of real numbers. So this symbol tell you everything about this set. So this is a general linear group of order 2 where the entries are being taken from the set of real numbers, right? So this is the set in this case. Now from this set, on this set we can apply the operation of matrix multiplication, because we are dealing with matrices here, right? So this is our operation, this is our set. Now we need to check whether this forms a group or not. So this forms a group, and in fact it is a non-abelian group. What does non-abelian mean? It means the property of commutativity does not hold, right? So let's check how this forms a group. So for that, we first of all require the closure property. Now that means, what does it mean? If we take 2 such elements of the kind and we multiply them, do we have this a matrix which also belong to this particular set? So the answer is yes. Why? Because if you multiply two matrices whose determinant is non-zero, say A and B, right? So because you know the determinant of A is not equal to 0, because we have chosen our A from this GL to A only, and we also select our B from this only. So therefore we have the condition that the determinants, they are not equal to 0. If determinant A is not equal to 0, determinant B is also not equal to 0. So that means their product is also not equal to 0. If this is not 0, this is not 0, so that means this is also not 0. So therefore we have determinant of AB also not equal to 0. So that means when you multiply these two matrices A and B, you will again get a matrix whose entries are real numbers, that is 2 cross 2, and moreover the determinant of that matrix is also non-zero. So therefore that matrix would also be a member of this particular set. So therefore the closure property hold in this particular case. Correct? Next is the property of associativity. Now for associativity, that is there for when you have matrices, because in case of matrix multiplication, you know, associativity holds. So therefore we are through with our two properties. For the third property of identity, this element, what is the determinant of this one? It is 1 into 1 minus 0 into 0, which is 1 only, right? So determinant is 1, which is not equal to 0. So therefore this belongs to GL2 comma R, right? And moreover, in addition, this is an identity. Why? Because if you multiply any matrix with this matrix 1 0 0 1, you will get back that same matrix. You can try, because this is the identity matrix. And moreover, last is the inverse of any random element. So let's consider a matrix whose entries are A, B, C, D. Now we wanted to calculate what is the inverse of this matrix. So we can calculate the inverse of this matrix by the known formulas from the previous classes. So the inverse is given by this thing. Now because AD minus BC in this case is non-zero, it is given to us. We initially considered this matrix, and the set here tell us that this determinant is non-zero. So therefore we have this as our inverse, right? So because it follows all the four properties, so therefore this is a group, and in fact it is a non-abelian group, right? Moving further on to the next example. Next we are taking the set of all 2 cross 2 matrices which have real entries. The set of all 2 cross 2 matrices with real entries. This is not a group. Can you suggest why? Just pause the video and tell me why this does not form a group under the same operation of matrix multiplication. It is because in this case, if you take all matrices A, B, C and D, in that case, if you wanted to calculate the inverse of this matrix, so you have two cases. If the determinant of this matrix, that means AD minus BC, if this is not equal to 0, then you can find the inverse. That is the property, right? But if the inverse is equal to 0, then you are not able to calculate the inverse of that matrix, and therefore in that case the fourth property does not hold, right? So therefore this does not form a group. Moving further, for the 11th example, now we are constructing another set. It also consists of 2 cross 2 matrices where A, B, C and D are member of F. Now what could be F? It could either be rational numbers, it could either be real numbers, it could either be complex numbers. So whatever initially you are taking, whichever set you are initially taking, either rationals, reals or complex, accordingly you will work further on the properties, right? So this F is a general term, it could represent anything. So SL2 comma R, it could be 2 comma R, it could be SL2 comma Q, right? It could be SL2 comma C, right? So okay, so what is this group? This set consists of all 2 cross 2 matrices such that the determinant in this case is equal to 1, right? This is the property. So we have a special name for this. This is a special linear group having all 2 cross 2 matrices, right, over the field F, where what is F? That is either Q or R or C, right? So this also forms a group, and it is also non-abelian group. So you should remember this thing, that SL2 comma F, that is a special linear group of 2 cross 2 matrices. So in this case also you can similarly check the closure property, you can check the associativity of this one, you can check the identity. Again, the identity would be the identity matrix only, right? And in this case also you can calculate the inverse. Why? Because the inverse here in this case is actually given to be 1, which is non-zero, right? So this forms a non-abelian group. Moving further on to the next example, the group GLNF, that is the general linear group of all n cross n matrices over F. So basically we are generalizing this the group that we have defined here. So it was a group which contained all the 2 cross 2 matrices having non-zero determinant, right? And we were calling this to be general linear group of 2 cross 2 matrices over R, and it was given by GL2 comma R. Now we are talking about general linear group GLN comma F, that is the general linear group of order n cross n over the given field F, right? So this is all for this video. You can now also create your own examples. I'll be discussing more examples in the next video. Well, that is it for this video. Thank you for watching.